Hello and welcome to this course on getting started with building Retrieval Augmented Generation applications. According to ZipRecruiter.com, developers with Retrieval Augmented Generation or RAG skills are likely to earn salaries at the higher end of the app developer spectrum. Typical compensation varies from approximately $127,500 to $180,000 or even more annually, depending on your experience, location, and demand. And Grandview Research reports that the RAG application market expects a compound annual growth rate of 49.1% through 2030, making RAG skills a valuable investment. Industries adopting RAG technologies include healthcare, finance, legal tech, e-commerce, education, manufacturing, energy, media and entertainment, telecommunications, and customer service. This hands-on course is designed for aspiring AI developers, machine learning engineers, data scientists, AI researchers, or someone in a related role. For course success, you need working Python programming skills and prior experience. Familiarity with LangChain, along with fundamental AI and web development knowledge, is also highly recommended. Next, let's examine what you'll learn. This course begins with Retrieval Augmented Generation, or RAG. You'll explore how this powerful technique combines the strengths of information retrieval and generative AI to produce accurate, context-aware responses. In the first hands-on lab, you'll use LangChain to split and embed documents and construct simple retrieval chains, all within a user-friendly Jupyter Notebook environment. In the second module, you'll transform your RAG knowledge into a working application by integrating LangChain with a large language model. You'll also develop an application by integrating LangChain with Gradio, enabling real-time interaction with your AI model. By the end of this module, you will have built a question and answer bot that retrieves answers from loaded documents, giving you hands-on experience with the full RAG pipeline from data to interface. In the final module, you'll explore LlamaIndex as an alternative to LangChain. You'll learn how to transfer your RAG skills across frameworks while building an icebreaker bot that helps users engage in meaningful conversations using both IBM Granite and LlamaIndex. You'll gain real-life experience working with vector databases, embedding models, chunking strategies, retrievers, and prompt templates. You'll complete this course with a solid understanding of RAG pipelines, the ability to develop projects using multiple frameworks, and the skills required to create full-fledged applications using Gradio, skills you can reuse for future projects. To get the most from this course, make sure you watch the videos, study each reading, check your understanding with practice quizzes, perform the hands-on labs, and test your knowledge with the graded assessments. Thank you, and all the best with this course. Welcome to this overview of the Professional Certificate in RAG and Agentic AI. AI is evolving beyond traditional models, enabling smarter applications. Retrieval Augmented Generation, or RAG, enhances AI's ability to provide accurate, context-aware responses by integrating real-time information retrieval. Multimodal AI is another advancement that allows systems to process and integrate various types of data, text, images, audio, and video, enabling more dynamic and interactive user experiences. Agentic AI represents a further shift, equipping systems with the ability to reason, plan, and autonomously execute tasks. While each of these approaches can work independently, they can also be combined to create more powerful and adaptable AI systems. Through this program, you'll gain the expertise to build and implement AI applications that combine these powerful techniques, preparing you for the next wave of AI-driven innovation. Whether you're looking to advance in software engineering, machine learning, or data science, mastering RAG, multimodal, and agentic AI will give you a competitive edge in the evolving job market. This RAG and agentic AI program consists of several short courses that cover generative AI applications, RAG applications, vector databases for RAG, advanced RAG with vector databases and retrievers, multimodal generative AI applications, AI agents, agentic AI fundamentals with LangChain and LangGraph, and finally, agentic AI with LangGraph, CrewAI, AG2, formerly AutoGen, and BAI framework. Each topic corresponds to an online course that you can complete independently. Each course consists of 2 to 3 modules. Completing courses covering different topics and the required projects will earn you the completion certificate. Let's look at the contents of each course. Your journey in the first course begins with the basics of generative AI, along with an in-depth look at prompt engineering, in-context learning, and prompt templates. You'll also be introduced to the LangChain framework to build generative AI applications, which streamlines AI workflows by enabling more structured and efficient prompt chaining. In the second course, you'll be introduced to the key components of Retrieval Augmented Generation, or RAG. You'll also learn how to implement RAG using LangChain. This course also introduces you to Gradio, helping you set up an interface to interact with AI models. Finally, you'll work with LlamaIndex as an alternative to LangChain, gaining hands-on experience building a bot with LlamaIndex and IBM's Granite model. The third course introduces you to the transformative role of vector databases in modern data management systems. You will gain insights into ChromaDB's architecture, common coding practices for its operations, and hands-on skills in performing basic vector operations. Similarity search is also explained with hands-on labs. Finally, you will build a recommendation system using a vector database and an embedding model. The next course provides a deep dive into advanced retrievers and retrieval patterns, equipping you with the skills to implement and optimize retrieval strategies within a RAG system. You will work with FACE, a powerful vector database used for efficient similarity search. You will also build a RAG application using FACE, LangChain, and Gradio. The fifth course begins with an in-depth introduction to multimodal AI, focusing on how AI systems process and integrate multiple data types. You will evaluate speech recognition and text-to-speech technologies, along with computer vision. You will work with tools such as OpenAI Whisper and Mistral to develop multimodal applications. You'll also explore how models like DALL-E generate images and the fundamentals of image captioning. Finally, you will dive into multimodal retrieval and search and multimodal question answering and chatbots, learning how cross-modal retrieval techniques enhance search engines and recommendation systems. The sixth course provides a detailed foundation for building AI agents. It covers function calling, chaining, and tool orchestration to enable AI systems to interact with external tools and execute tasks effectively. You'll also learn how to manually handle tool calls by parsing the outputs of language models. Finally, you will leverage LangChain's built-in agents, including data frame and SQL agents, to analyze structured data, generate visualizations, and perform database queries through natural language. The seventh course helps you use LangGraph and LangChain to develop stateful workflows. You'll explore key architectures such as agents and React agents, applying them to real-world applications. Additionally, the course introduces multi-agent system design and agentic RAG architecture, equipping you with skills to build scalable, robust applications. The eighth and final course helps you design AI workflows using state-of-the-art design patterns and multi-agent orchestration frameworks. You will be introduced to agentic frameworks such as Crew AI and LangGraph. Finally, you will dive into alternative agentic frameworks, IBM's BAI framework, and AG2 to implement multi-agent collaboration and conversation-driven systems. This program presents you with practice and graded quizzes to evaluate your learning. The graded quizzes carry a weightage that contributes to the course completion. These courses have hands-on labs and projects that contribute to the course and program completion requirements. Finally, after you have successfully completed all of the courses, you will be awarded the completion certificate for this IBM program, a credential valued by many employers. We wish you the very best and hope you enjoy this journey.
Large language models, they are everywhere. They get some things amazingly right and other things very interestingly wrong. My name is Marina Danilevsky. I am a senior research scientist here at IBM Research, and I want to tell you about a framework to help large language models be more accurate and more up-to-date. Retrieval Augmented Generation, or RAG. Let's just talk about the generation part for a minute. So forget the retrieval augmented. So the generation, this refers to large language models, or LLMs, that generate text in response to a user query referred to as a prompt. These models can have some undesirable behavior. I want to tell you an anecdote to illustrate this. So my kids, they recently asked me this question. In our solar system, what planet has the most moons? And my response was, oh, that's really great that you're asking me this question. I loved space when I was your age. Of course, that was like 30 years ago, but I know this. I read an article, and the article said that it was Jupiter and 88 moons. So that's the answer. Now, actually, there's a couple of things wrong with my answer. First of all, I have no source to support what I'm saying. So even though I confidently said, I read an article, I know the answer, I'm not sourcing it. I'm giving the answer off the top of my head. And also, I actually haven't kept up with this for a while, and my answer is out of date. So we have two problems here. One is no source, and the second problem is that I am out of date. And these, in fact, are two behaviors that are often observed as problematic when interacting with large language models. They are LLM challenges. Now, what would have happened if I'd taken a beat and first gone and looked up the answer on a reputable source, like NASA? Well, then I would have been able to say, okay, so the answer is Saturn with 146 moons. And in fact, this keeps changing because scientists keep on discovering more and more moons. So I have now grounded my answer in something more believable. I have not hallucinated or made up an answer. Oh, and by the way, I didn't leak personal information about how long ago it's been since I was obsessed with space. All right, so what does this have to do with large language models? Well, how would a large language model have answered this question? So let's say that I have a user asking this question about moons. A large language model would confidently say, okay, I have been trained, and from what I know in my parameters during my training, the answer is Jupiter. The answer is wrong, but, we don't know. The large language model is very confident in what it answered. Now, what happens when you add this retrieval augmented part here? What does that mean? That means that now, instead of just relying on what the LLM knows, we are adding a content store. This could be open, like the internet. This could be closed, like some collection of documents, collection of policies, whatever. The point, though, now is that the LLM first goes and talks to the content store and says, hey, can you retrieve from me information that is relevant to what the user's query was? And now, with this retriever augmented answer, it's not Jupiter anymore. We know that it is Saturn. What does this look like? Well, first, user prompts the LLM with their question. They say, this is what my question was. And originally, if we're just talking to a generative model, the generative model says, oh, okay, I know the response. Here it is. Here's my response. But now, in the RAG framework, the generative model actually has an instruction that says, no. First, go and retrieve relevant content. Combine that with the user's question, and only then generate the answer. So the prompt now has three parts. The instruction to pay attention to the retrieved content, together with the user's question, now give a response, and in fact, now you can give evidence for why your response was what it was. So now hopefully you can see, how does RAG help the two LLM challenges that I had mentioned before? So first of all, I'll start with the out-of-date part. Now, instead of having to retrain your model if new information comes up, like, hey, we found some more moons. Now it's a Jupiter again, maybe it'll be Saturn again in the future. All you have to do is you augment your data store with new information, updated information. So now the next time that a user comes and asks the question, we're ready. We just go ahead and retrieve the most up-to-date information. The second problem, source. Well, the large language model is now being instructed to pay attention to primary source data before giving its response, and in fact now being able to give evidence. This makes it less likely to hallucinate or to leak data because it is less likely to rely only on information that it learned during training. It also allows us to get the model to have a behavior that can be very positive, which is knowing when to say, I don't know. If the user's question cannot be reliably answered based on your data store, the model should say, I don't know, instead of making up something that is believable and may mislead the user. This can have a negative effect as well, though, because if the retriever is not sufficiently good to give the large language model the best, most highest quality grounding information, then maybe the user's query that is answerable doesn't get an answer. So this is actually why lots of folks, including many of us here at IBM, are working the problem on both sides. We are both working to improve the retriever, to give the large language model the best quality data on which to ground its response, and also the generative part so that the LLM can give the richest, best response finally to the user when it generates the answer. Thank you for learning more about RAG.
Welcome to Retrieval Augmented Generation, or RAG. After watching this video, you'll be able to explain the RAG process. You'll also be able to describe various steps in the RAG process to receive efficient responses to questions or prompts you enter. Let's first understand what RAG is. RAG is an AI framework that helps optimize the output of large language models, or LLMs. RAG uses the capabilities of LLMs in specific domains or the internal database of an organization without retraining the model. Pre-trained LLMs may face challenges with specific domain knowledge that they are not trained in. While they perform well on general tasks, they may provide inaccurate responses to specialized queries. Therefore, adding external, relevant knowledge sources helps ensure more accurate responses. Consider an example of a company's mobile policy. If you ask a chatbot about the company's mobile policy, the chatbot will provide answers from its knowledge base because the company's policy contains confidential information. Therefore, to generate domain-specific responses, the RAG process is helpful. Let's explore how RAG helps in generating responses. Based on the inserted content or prompt, RAG combines retrieved information and generates natural language to create responses. RAG uses various content from its knowledge base, including data from the trained chatbot, company policies unavailable on the internet, and large documents. RAG consists of two main components: the retriever, the core of RAG, and the generator, which functions as a chatbot. In the RAG process, the first step is text embedding. The inserted prompt or question is converted into a high-dimensional vector using a question encoder. Knowledge-based documents are separately converted into high-dimensional vectors and embedded using a content encoder. The next step is retrieval, where the system matches the similar vectors in the inserted prompt or content with the vectors in the knowledge base to retrieve information. However, in the augmented query creation, the system creates an augmented query by combining the text associated with the retrieved vectors and the original prompt or content. Lastly, in the model generation step, the language model uses the created augmented query to generate a response using the content from the knowledge base. The encoders convert the prompt and knowledge base into embeddings that represent the information. Then, the context and question embeddings can be generated from the same encoder. This approach is easy to understand as it involves converting text to embeddings, even though it may not work as effectively. Now, let's understand prompt encoding. The inserted prompts use token embedding and vector averaging to encode the prompts and convert them into a vector representation. In the token embedding, each token, such as a word or subword, inserted in the prompt uses a pre-trained token embedding model, such as bidirectional encoder representations from a transformer or BERT, and a generative pre-trained transformer or GPT to transform into a high-dimensional vector. Once all the tokens are embedded, the system takes the average of all token vectors to create a single vector representation for the prompt. This means that the averaged vector representation captures the meaning of the inserted prompt in a concise manner. Next, let's understand how to convert the contextual data from the knowledge base into vectors. Consider the company's mobile policy displayed on the screen. You can see that the company's mobile policy is large and inserting it into the chatbot may be challenging. Therefore, the original policy document should be broken down into smaller, manageable chunks of text to achieve targeted and efficient retrieval. Next, embed each text chunk into vectors and index them into a knowledge base. Now encode the text chunks for vector representations by transforming them into a high-dimensional vector using a pre-trained token embedding model. Once all the tokens are embedded, the system averages each token vector to create a single vector representation for the entire text chunk. Combining text chunks and embedded vectors represents the knowledge base, which captures the information for each chunk. Insert these embeddings into a vector database to represent the knowledge base with the chunk ID that serves as the key. The distance operations on these embeddings use chunk ID to find relevant information. The next step in the RAG process is to search for relevant context for the inserted prompt from the knowledge base. To do so, the system compares the prompt vector with the vectors representing the text chunks in the knowledge base. Let's ask a question about a company's mobile policy. The knowledge base and question are converted into vector representations. Further, the system calculates the distance between the prompt vector and each context vector using distance metric to identify the similarities between the prompt vector and the context vector. Next, it selects 3 to 5 context vectors close to the prompt vector to present more relevant information to augment the inserted input using distance metrics. Let's take query embeddings Q and embeddings from the knowledge base as C1 and C2. The selected distance metrics affect the retrieval results. If you take a dot product, considering vectors' directions and magnitude by prioritizing overall alignment, you will find knowledge-based embedding C2 slightly closer to the context vector. Now, consider the cosine direction, which focuses on the direction to measure the angular difference. Therefore, the knowledge-based embedding C2 is a good option. It means that for the vector magnitude, the dot product is preferable, and for the direction vector, the cosine distance is preferable. To select the most relevant top K context, where K is the hyperparameter, choose the chunk IDs 6, 2, and 0 using the company's mobile policy with 7 chunks. The real dataset uses the library of chunks to speed up the process. This means you should select the text chunk IDs similar to the query and related to the company's mobile or general company policies. Finally, the selected text from the knowledge base and the query are inserted into the chatbot to generate an appropriate response. This means that with the help of RAG, the chatbot can provide an efficient response. In this video, you learned to leverage RAG to generate a response when the model is not pre-trained. The chatbot generates responses based on the questions. However, it is challenging to generate responses for specific domains, such as the company's mobile policy. To generate a response for the company's mobile policy, the inserted prompts are encoded using token embedding and vector averaging, where the prompt is broken down into smaller and possible chunks of text. These chunks are embedded and converted into high-dimensional vectors to search for the relevant context using distance metrics. The vector closest to the text chunk is selected from the knowledge base to generate an appropriate response. Welcome to Getting Started with Gradio. After watching this video, you'll be able to describe what Gradio is and explain how to set up a Gradio interface for model interaction. Gradio is an open-source Python library for creating customizable web-based user interfaces. It is designed for ease of use, especially for machine learning models and computational tools. Let's take a step-by-step look at how it works. First, you write the Python code to define the functions and logic for your application. Next, you use Gradio to create an interface for these functions. Here, you use Gradio's interface class to specify the inputs and outputs for your functions. Then configure the interface to define how users will interact with your application. The next step is launching the Gradio server using the launch method. This starts a local server on your machine, creating a web interface for your application. As the final step, you have access to the web interface through a local or public URL provided by Gradio. Users can interact with the interface, providing inputs and receiving outputs in real time. First, you need to install the Gradio package using pip. Once installed, you can import Gradio as GR. Now let's code a simple Gradio interface that has a text input field and then displays the entered text as output. The GR interface function is a core component of the Gradio library. It creates interactive web interfaces for Python functions with customizable input and output components. You then define the function to be executed once the user enters the query. Here you can define any functionality according to the use case. In this case, you are just returning the entered text. GR text box is used to create a text box wherein you can also define a custom label for the text box. Similarly, you create a text box for the output. Using launch, you can then run the interface. Here is the Gradio interface you get from the code. As you can see here, there are 2 text boxes, one for input and one for output. Let's see how you can have multiple inputs in the Gradio interface. Just like GR textbook is used to create a text field in the same way, GR number is used to create a numeric field. You can pass GR number and GR textbook as a list of inputs. Similarly, if you want to add more inputs, you can add them here in the input list. Now let's see the output from the generated code. You can observe that you now have 2 types of inputs, one for text and one for numeric values. You can also create an option to upload or drop files with Gradio. Here is a code to count the number of files uploaded by a user. grfile allows users to upload files in a web interface. It supports multiple file uploads and provides paths to uploaded files for further processing in the backend function. You then define the count files to calculate the number of files uploaded by the user. Once you launch the code, it generates a unique web interface link which can be used from anywhere until the session is running. You now have the option to upload or drop the files through a web interface. Let's recap. In this video, you learned that Gradio is an open-source Python library for creating customizable web-based user interfaces. To set it up, you have to write the Python code, create the Gradio interface, launch the Gradio server using the launch method, and access the web interface through a local or public URL provided by Gradio. You learned that to code a simple text input and output with the Gradio interface, you can use the Gradio interface function. Finally, you learned that to upload or drop files with Gradio in a web interface, you can use the gr file. Welcome to this video that introduces you to LlamaIndex document ingestion and chunking. After watching this video, you'll be able to describe LlamaIndex, including some of its typical use cases, explain how LlamaIndex works with RAG, load source documents from a variety of formats into LlamaIndex's document class, and split documents into chunks or nodes using LlamaIndex. Let's begin with a high-level overview of LlamaIndex. LlamaIndex is a framework for building LLM-powered context augmentation. Context augmentation is the process of making your data available to an LLM, allowing the LLM to perform a particular task while grounding its responses in the provided context. Typical use cases include question answering with Retrieval Augmented Generation, or RAG, which is the primary focus of this video. Chatbots, which extend the basic RAG pipeline by allowing for multiple back-and-forth queries and answers, allowing the LLM to ask for clarification or answer follow-up questions. And document understanding and data extraction, which allow an LLM to read natural language and semantically identify important details such as names, dates, addresses, and figures from large amounts of structured or unstructured data. Let's learn how LlamaIndex works in the context of Retrieval Augmented Generation, or RAG, because many of LlamaIndex's other use cases depend on or are related to components used in RAG. The RAG process begins by loading and chunking the source documents. These document chunks are then embedded using the embedding model, which embeds text as equal-sized vectors, one vector per text chunk. These vectors then go into a vector store, which is a database that is well suited to storing and manipulating vectors. When a prompt is provided by the user, that prompt is then embedded using the same model as the source documents, and a retriever is used to retrieve the relevant text from the vector store. The retrieved text is then used to augment the prompt, and this augmented prompt is then fed into an LLM to provide a context-aware response that considers the most relevant data from the source documents. Let's begin with the first RAG step, which involves loading textual data file objects into a LlamaIndex document, which is LlamaIndex's generic container for document sources. You can load textual data from a variety of formats, including text files, PDF files, Markdown files, comma-separated or CSV files, JSON files, and HTML files. In addition to supporting the loading of local documents, LlamaIndex also offers numerous connectors for seamless integration with various databases and cloud storage services. Let's quickly examine LlamaIndex's document class and some of its unique features. First, you create an object of the document class by passing the text "Hello LlamaIndex" into the document class's text parameter. Then, by calling the resulting document object's dict method, you can inspect the items stored in the document. Note that a LlamaIndex document has several key components: an ID that uniquely identifies the document, a placeholder for embedding if you decide to embed the whole document, a metadata dict where you can store metadata associated with the document, such as its origin or date of creation, a relationships dict that links the document to other related items such as other documents, and the text that is present in the document. Thus, the document class serves as a container that stores a document's text in addition to providing each document with a unique ID and stores the document's metadata and relationships in dictionaries. Now, let's look at how to load documents from local storage. LlamaIndex provides a powerful document loader called Symbol Directory Reader that can load many file types, including plain text, Markdown, CSV, and PDF files. To use the Symbol Directory Reader file loader, import it from llama_index.core. Then you can load all files in the directory by passing that directory's path as the first argument to Symbol Directory Reader and calling the load_data method. If, on the other hand, you would like to load all files from a path with all of its subdirectories, you can pass recursive equals true as a parameter to Symbol Directory Reader. Alternatively, if you would like to load specific files, you can pass the file's path as a list to the input_files parameter. Finally, to load specific file types only, pass a list of requested file type extensions to the required_ext parameter. Note that Symbol Directory Reader outputs a list of LlamaIndex document class objects of the type you just saw. A LlamaIndex node is simply a text chunk. Chunking long text helps retain the specific context of each segment, leading to more precise and relevant embeddings. LlamaIndex provides an easy-to-use but surprisingly effective text chunker called Sentence Splitter. Sentence Splitter uses a recursive method, splitting long text successively based on specific characters such as new line characters and periods. To use Sentence Splitter, first import it from llama_index.core.node_parser. Then, define the node parser by passing the chunk_size and chunk_overlap parameters. The chunk_size parameter controls the maximum size of each chunk in tokens, and the chunk_overlap controls the maximum number of tokens that can overlap from one chunk to the next. Then use the get_nodes_from_documents method to split documents into individual nodes. Note that the node parser returns a list of LlamaIndex text node instances, which are similar in structure to the structure of LlamaIndex document instances that you saw previously. In addition to Sentence Splitter, LlamaIndex provides many other splitters, such as Semantic Splitter that splits wherever sentence similarity falls below a certain threshold, or a wrapper for LangChain splitters that allows you to use any LangChain splitters in LlamaIndex. Next, let's summarize what you've learned so far. You learned that LlamaIndex is a framework for building LLM-powered context augmentation. Typical use cases for LlamaIndex include question answering using RAG, chatbots, document understanding, and data extraction. In the first RAG step, LlamaIndex loads source documents by converting text, PDF, Markdown, CSV, JSON, and HTML files into LlamaIndex document objects. The LlamaIndex document class creates a document object with several key components, including a unique ID, an embedding placeholder, a metadata dictionary, a relationships dictionary for linking to other documents, and the text in the source document. You can use LlamaIndex's Symbol Directory Reader to import and load files from a folder, its subdirectories, specific files, and specific file types. You can use LlamaIndex's Sentence Splitter to divide documents into chunks based on predefined separators, and you can also chunk documents using other splitters, such as Semantic Splitter, or by using a wrapper around any LangChain splitter. Welcome to this introductory video about LlamaIndex that covers topics from vector stores to query engines. After watching this video, you'll be able to discuss embedding and vector stores in LlamaIndex, describe how retrieval works in LlamaIndex in the presence of a vector store, discuss prompt augmentation and LLM querying in LlamaIndex, and explain how LlamaIndex's powerful query engines combine several RAG steps into a single object. Let's start with a high-level review of RAG. In Retrieval Augmented Generation, documents are loaded, chunked, and embedded into vectors stored in a vector store. A user prompt is also embedded, and similar chunks from the source documents are retrieved from the vector store. The prompt and retrieved text are combined and sent to a language model to generate a context-aware response. By now, you're already familiar with loading and chunking documents into nodes. Let's begin with embedding those nodes and storing them in a vector store. Let's look at how you can generate embeddings. To generate and store embeddings, LlamaIndex uses the Vector Store Index class. For simple use cases, the embeddings can be generated using a default model and stored in memory by simply passing in the nodes as the only parameter to Vector Store Index. For more complex cases that require a custom embedding model and persistent storage, the following procedure is needed. First, import the necessary libraries. In this case, you are importing the ChromaDB vector database to store the embeddings and a function that imports embedding models from Hugging Face. Then define the embedding model. In this case, you are using an embedding model from Hugging Face. Next, set up your vector store and storage context. In this case, you are using ChromaDB and then passing the embedding model and storage context into vector store index. Then pass the nodes, the embedding model, and the storage context into vector store index to generate embeddings using the selected model and to store the embedding vectors inside the persistent storage defined by the storage context. Thus, whether you store embedding vectors in memory or in persistent storage, LlamaIndex's powerful vector store index class efficiently handles both embedding text chunks and storing the resulting embeddings in the vector store. Given a vector store index, the user's original prompt embedding and retrieval steps can be combined in LlamaIndex using the following process. First, create the retriever by calling the as_retriever method on the vector store index object. Then pass the user's prompt to the retriever object's retrieve method to obtain the relevant results. Alternatively, if you need to control the maximum number of items retrieved, specify the maximum number of retrieved items by setting the similarity_top_k parameter when creating the retriever object. When the user's prompt is passed to this retriever, it retrieves the k nodes most similar to the user's prompt from the vector store, which in this case would be 5 nodes. The retrieved nodes are returned as a ranked list with the most similar nodes at the top of the list. Let's now discuss prompt augmentation, LLM querying, and response generation. LlamaIndex has the ability to combine the prompt augmentation, LLM querying, and response generation RAG steps using a response synthesizer. Given a user's prompt and retrieved nodes, the response synthesizer's synthesize method generates a response from the LLM. Note that the embedding of the user's prompt augmentation, and the passing of the augmented prompt to the LLM are done in the background, and no additional steps have to be taken by the user to perform these steps manually. With LlamaIndex, the process can be simplified even further using a query engine. LlamaIndex's query engine combines the prompt embedding, retrieval, prompt augmentation, LLM querying, and response generation steps, eliminating the need to manually retrieve nodes and to pass them to a response synthesizer. Given a user's prompt, the query engine's query method generates a response from the LLM. Note that the embeddings of the user's prompt, retrieval, prompt augmentation, and the passing of the augmented prompt to the LLM are done in the background, and no additional steps have to be taken by the user to perform these tasks manually. As a result, LlamaIndex's query engines greatly reduce the amount of code that needs to be written when building a RAG application. And remember these helpful tips when creating your application. You can customize a LlamaIndex query engine by changing the default LLM to a different one of your choosing, defining a custom prompt template for prompt augmentation, or by specifying a custom retriever. LlamaIndex provides numerous avenues to customize the RAG process to fit the needs of your application. Let's review what you've learned. In this video, you learned that LlamaIndex uses the vector store index class for embedding generation and storage. You create the retriever by calling the as_retriever method on the vector store index object. Then you pass the user's prompt to the retriever object's retrieve method to obtain relevant results. The response synthesizer in LlamaIndex combines prompt augmentation, LLM querying, and response generation in one step. The response synthesizer uses the original prompt and retrieved nodes to generate a response, refining it if needed with leftover nodes. You can customize response synthesizer behavior using different LLMs or prompt templates. A query engine can compress the process further by combining the prompt embedding, retrieval, prompt augmentation, LLM querying, and response generation RAG steps into a few simple commands, and a query engine can be modified by changing the default LLM, customizing the prompt template, or modifying the retriever. Congratulations on completing this course. You now have a comprehensive understanding of how to get started with RAG with Gradio and LlamaIndex. Next, it's time to explore opportunities to continue learning and applying your new skills. But before that, let's review some key concepts you learned throughout this course. You learned that Retrieval Augmented Generation, or RAG, is a machine learning technique that combines information retrieval with generative AI to produce accurate, context-aware responses. RAG improves LLMs by integrating external or domain-specific knowledge without retraining, helping them generate more specialized and accurate outputs. You learned that RAG consists of a number of steps, which can be summarized as: first, during text embedding and prompt encoding, prompts and documents are broken into chunks and transformed into high-dimensional vectors using AI models such as bidirectional encoder representations from transformers, known as BERT, and generative pre-trained transformers, or GPTs. Next, during retrieval, relevant document vectors are retrieved based on distance metrics such as dot product or cosine similarity. Then, during augmented query creation, the retrieved content is combined with the user's prompt. And finally, during model generation, the system uses the augmented prompt to generate an informed, accurate response. You also now know that RAG consists of two main components: the retriever and the generator. The retriever finds relevant data from a knowledge base, and the generator uses the retrieved data to produce natural language responses. Developers and data scientists use RAG because RAG retrieves only the most relevant information, ensuring responses are accurate, domain-specific, and up-to-date without retraining the model. And you know that RAG enables chatbots and AI systems to deliver specialized, trustworthy answers by integrating external knowledge, making them reliable for industry-specific or confidential topics. Next, you learned about how Gradio, an open-source Python library, can create customizable web-based user interfaces, particularly for machine learning models and computational tools. You can share Gradio interfaces through unique URLs, facilitating easy collaboration and feedback collection. Setting up a Gradio interface consists of 4 steps: writing Python code, creating an interface, launching the web server, and accessing the web interface. Gradio provides the following tools you can use to build capabilities into a web app. gr.textbox enables users to type text into the app or display text from the app. For example, you can use the gr.textbox with chatbot apps for users to type questions and see answers. Next, gr.number lets users enter numbers. For example, a calculator app can use gr.number to let users type numbers for math operations. Finally, gr.file lets users upload files into an app. You also now know that LlamaIndex is a flexible framework for building LLM-powered applications that focuses on context augmentation through structured document ingestion, chunking, indexing, and retrieval. Use cases for LlamaIndex include question answering using RAG for chatbots, document understanding, and data extraction. LlamaIndex offers built-in document loaders and customizable query engines, unlike LangChain, which emphasizes chaining steps and workflows. To design a conversational RAG app with LlamaIndex, ingest the data, chunk the data into nodes, embed and store the data as vectors, and use a response synthesizer or query engine to generate personalized responses from user prompts. You can apply the RAG pipeline, loading, chunking, indexing, and querying using LlamaIndex's document, node, index, and query engine classes. LlamaIndex loads source documents by converting text, PDF, Markdown, CSV, JSON, and HTML files into LlamaIndex document objects. The LlamaIndex document class creates a document object with several key components, including a unique ID, an embedding placeholder, a metadata dictionary, a relationships dictionary for linking to other documents, and the text in the source document. You can use Simple Directory Reader to import and load files from a folder or its subdirectories, import specific files, or import specific file types. You can use LlamaIndex's sentence splitter to recursively split documents into chunks based on predefined separators. You can also chunk documents using other splitters, such as Semantic Splitter, or by using a wrapper around any LangChain splitter. We encourage you to extend your learning and apply this course toward an IBM professional certificate. Depending on your schedule and the number of courses in the program, you can complete this professional certificate in approximately 2 to 6 months. You'll find the links to the professional certificate and several related courses in the Congratulations and Next Steps reading at the end of this course. We recommend that you continue to apply the knowledge of RAG you gained from this course in your work. We hope your new skills support your work and enable you to advance professionally. Congratulations on completing this course. We appreciate your participation in this learning journey and wish you all the best.